Hello friends, welcome to problem 5 of the Stat 111 final exam live solve. Um, yeah, so let's get right into it. I hope you guys take a look at this problem beforehand and take a stab at it before coming to this video. Okay, so a traffic safety engineer is studying the car accident rate in his state. He collects data on the number of car accidents in a particular 1-year period in N different counties. Let YJ be the number of car accidents in County J, and C sub J be the number of people who live in County J. Suppose YJ is distributed Poisson C sub J theta, where C sub J are known and theta, the underlying car accident rate per person is estimated. So we're looking for theta, the per person car accident rate. Okay, so first we need to find the MLE theta hat of theta. So as usual, we compute the likelihood. So we have a bunch of these YJs distributed Poisson C sub J theta. So we want to have the joint distribution of that. So first we go likelihood theta given the data. This is equal to the joint PDF of the data given theta equal to this product. Since the counties are independent of one another, and then this is the product, since we have Poissons, of e to the negative c sub j theta, c sub j theta to the yi over yi factorial. But this denominator is going to go away due to proportionality. So this is proportional to this. And then if we get rid of all of the, so for example, or I guess let's try to bring the product in. So this is going to be equal to e negative theta sum of the c sub j's. And then we have, well, the c sub j, y sub I term, this is going to go away since that's just of the known c sub j's and the yi, the data. So we just want the theta. So this is going to be theta sum of yi's. So here is our likelihood. Now we're going to take the log of that for the MLE. So log likelihood is equal to negative theta sum Cj plus log sum Yj log theta. Taking the derivative of that, so dl d theta equals negative c sub j plus y sub j over theta. Setting this equal to 0 implies that this is theta hat will equal sum of the yj's over sum of the cj's. So here is our MLE. Okay, so now we want to find the standard error of theta hat. So the standard error is going to be the standard deviation of the estimator theta hat. So we're going to go variance theta hat is equal to variance of this stuff. And then we can, all of the YJs are going to be independent of one another since they're different counties. So we have sum of CJs squared, sum of variance YJs. And each one of these YJs, remember they're Poisson C sub J theta. So that has variance C sub J theta. So then this is going to turn into theta times the sum of C sub J over the sum of C sub J squared. And this will in total become theta over a sum of C sub j. So that's going to be the variance. So our standard error is the square root of that. So it's going to be square root of theta over a sum of C sub j. And if you want to be precise, all of these sums are going to be from j equals 1 all the way to n. You should be precise. I guess I just wrote that because laziness. Okay, so next question asks, find a one-dimensional sufficient statistic S. Is it possible to Rao-Blackwell with respect to S to obtain an estimator for theta whose MSE is strictly smaller than theta hat? If so, compute it. If not, why not? So let's look for a sufficient statistic S. So we're looking for something that the data and the parameter are attached to one another. So this is going to be, if we look at the likelihood here, the data is right here and it's attached to the theta. So if we know this function of the data, it's the only place that it appears in this likelihood. So we would be able to compute this likelihood from just this sum. So our sufficient statistic S is sum of the y sub j's, j equals 1 to n. So that's our sufficient statistic. And now we want to determine whether we can Rao-Blackwellize the MLE. So this guy here, we will not be able to Rao-Blackwellize it because what Rao-Blackwellization will do is take this theta hat and condition it on S. But right now our theta hat is S over that like some constants. And we would be able to like take out what's known and it would just be the same MLE. So no, because MLE is a function of S. Okay. So for D, we're going to transition into a Bayesian perspective. So now we have, well, we already had this like yj given theta is Poisson this. This time we're adding a prior of theta is distributed as gamma r naught p naught. So we're looking for, let's find the posterior mean of theta given the data. So we want to find the posterior distribution of theta. So this is the Poisson-Gamma conjugacy, and it is going to tell us that the posterior is distributed gamma with some parameters. So let's figure out what the parameters are. I don't have this one memorized. I have beta binomial memorized, but it's going to be a similar idea. So we have posterior is going to be proportional to likelihood times the prior. And we know that the likelihood is, we wrote it up here, it's this guy, e to the negative theta sum of c sub j's, and then c sub j's, or theta to the y, sum of y sub j's. So that's the likelihood. And now for the prior, we're going to look at the table of distributions. So the table of distributions tells us the PDF is this like going to be gamma times some stuff. Well, we only care about the things that are attached to X. So we have lambda, so B naught. Yeah, B naught theta to the R naught, and then e to the negative E naught theta, and theta to the negative 1. So this taking the proportionality, we only care about the stuff with thetas in it. So it's going to be theta R naught minus 1 e to the negative b theta. Yeah, so that's going to be our prior. And if we combine that, we get e to the negative theta sum of c sub j's minus plus b, and then theta to the sum of yj plus r naught minus 1. So if we go back to this, we have, this is now going to be a gamma, and our first parameter is going to be this stuff here. So sum of yj plus r naught. And the second parameter is going to be this stuff here. So comma sum of c sub j plus b naught. Yeah, so that's our new posterior distribution. And the mean of that is going to be this first term over the second term. So our mean, I move this up just a little bit. Our mean is going to be expectation theta given y is equal to sum of yj plus r naught over sum of cj plus b naught. So this is going to be our answer for this part. Okay, and then the final question says, a new county with c sub n plus 1 residents is added to the survey, or to the study. Find an approximate 95% predictive interval for for the number of car accidents in the new county for within a year period. And this is all going to be given the previous data. Okay, so we saw in like one of the P sets before, basically what we're looking for is we're looking for kind of the posterior distribution of this new yn plus 1. And we have that the theta right now, the theta given y1 dot 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 yn, this is distributed gamma sum yj plus r naught, comma sum cj plus b naught. And if you look in the Stat 110 textbook, or on the, I forgot which preset, on page 439 on example, is it 439? Yeah, 439, example 9.6.3 gamma Poisson revisited. We have that the marginal PDF of the, when we have the setup, our setup is going to be, we have, like, in this case, theta is distributed gamma r naught b naught, and y given theta is distributed Poisson theta c sub j yj. And then this tells us that our y marginally is distributed negative binomial r naught comma b naught over b naught plus c sub j. So that's in the prior, but wow, now we have like this posterior. So now we have y sub n plus 1 is distributed y1 dot 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 yn, distributed negative binomial sum of yj plus r naught, comma sum of cj plus b naught over sum of cj plus b naught plus c n plus 1. Here's, I run out of room, so I'm going to move this. plus Cn plus 1. So this is going to be our posterior distribution, posterior predictive distribution. And now we can construct the posterior predictive interval by taking the 0.025th quantile and the 0.975 quantile. So we want like Q and bind 0.025 and then like some y j plus r naught, comma, some, perhaps maybe a better way. Let's do like Q and bind, let's call this A, call this B, AB of 0.025, comma, Q and bind AB of 0.975. And this is going to be our positive posterior predictive interval. And you should note that this Qn bind is the quantile function for the negative binomial with these parameters. Okay, fantastic. So that was problem 5. Hope you enjoyed that. And good luck studying for the final. Maybe in the next problem, I'll go find the cat again. See you guys.